Cape Town in South Africa. The title of the talk is Role of CO and Water on the Stability of Cobalt Fischer-Tropsch Catalyst. It's presented by Professor Micheal Claeys.
Great. Thank you very much for the introduction, and also like to thank the organizers for giving me the opportunity to present today. It's about cobalt, so a switch from iron here. This work was conducted under the synthesis gas program of C-Change at DSD NRF Center of Excellence Catalysis, which is hosted by the University of Cape Town. It's a national South African center. As any other catalyst, cobalt-based Fischer-Tropsch catalysts are plagued by deactivation processes. These are listed here, some of those. And I will focus on the first three of them, which are the most prominent ones and which cause a lot of problems to your catalyst, particularly the first two, sintering oxidation. So we want to try and understand how these come about. We would like to run at very high conversion levels, but often we're limited in terms of the commercial Fischer-Tropsch processes to certain limits here, around about 75% maybe. We would like to operate at much higher conversion levels, but there are problems, and this is associated with the presence of large amounts of water. It needs to be seen in conjunction with the reaction conditions, as I will point out throughout my talk. Also, the water to hydrogen ratio I want to introduce at this point here, which obviously corresponds to a conversion that we have. Some examples from literature about sintering. This mechanism here was put forward, crystallite migration, where we have crystallites migrating, they meet, they coalesce, they form larger crystallites, and then they re-reduce, and in doing so, they have lost a lot of the surface area. And this is facilitated by oxygen species on the surface. That's what several authors have claimed, but no direct proof has been provided. We've also done some work, and this is in conjunction with Cecil, a long-standing partner of ours, where we looked into sintering as a function of reaction conditions, where we varied CO and water at partial pressures over quite a wide range. This is an alumina-supported cobalt catalyst. And what we did here is a couple of experiments. These are nine experiments that we did in total here. We started off with a water to hydrogen atmosphere, and then we blend in carbon monoxide, and you can see that sintering occurs. We're showing a sintering parameter, which I will introduce to you in a short while. You can see two things. Firstly, once you're introducing carbon monoxide, you can observe sintering. So it's clearly carbon monoxide-induced sintering that we see here, but in the presence of water. And you can also see that a combination of water and hydrogen, water and CO gives you more severe sintering than lower percentages of those partial pressures. This was after 3 hours here. We continued scanning the behavior of this catalyst over many hours, 48 hours, and this goes on and on. There's also some post-run TM analysis which we conducted. So what we believe is happening here is that we have CO-assisted sintering on a modified alumina surface, modified in terms of water, which impacts on the surface and forms OH species. What we do believe is happening is an Oswald ripening mechanism where we have this modified surface and we have subcarbonyls of cobalt, which are mobile on this modified surface now, and you can get Oswald simple ripening to go. This is further supported by computational work which was done also in our collaboration with Cecil. As for oxidation, bulk cobalt should not oxidize, or only at a ratio of larger than 130, which is basically 100% conversion. But small crystallites can oxidize. It was calculated by my colleague, Mr. Constein, who's also in the audience here, because smaller crystallites have different surface energy properties. And indeed, it was predicted that small crystallites of FCC can undergo oxidation at certain conditions. So at the time when we started looking into that, a couple of years ago, there was not a lot of information around where there was evidence for this oxidation process. This is some in situ work which we found in literature, which we found most trustworthy at the time, but none of them had touched this line where we would have expected oxidation. Some words about strong metal support interactions, and I believe there's going to be more in a talk later on from the Trondheim group here. This is in situ Zane's works with rhenium-modified cobalt alumina catalysts, where you can see not only oxidation to cobalt oxide, but also the formation of cobalt aluminate was very nicely shown in this in C2 work here. This is the mechanism which was put forward by the authors. After reduction, you have differently sized crystallites here. Some cobalt spreading has happened already, cobalt aluminate formation. But in the spent catalyst, it was assumed or deduced that small crystallites have oxidized and metal support interaction has happened after that. In these experiments that I want to show you now, there's some examples that we use in order to deconvolute those effects and learn more about sintering, oxidation, and metal support compound formation. And we do this via development of monocatalysts, so different monocatalysts that we have prepared specifically for this, the choice of different supports, and also the choice of selection conditions. We make use of our in situ magnetometer mostly in most of these experiments that I show you. It's a piece of equipment that we have developed with Sasol R&D. It's been put to use for a number of years now already. We typically mimic high conversion conditions via feeding water. So we run in low conversion conditions overall, and then we mimic higher conversion conditions via addition of water. What we have in this piece of equipment, which can go up to 900 degrees and 50 bar, is a reactor which oscillates in a magnetic field, the field strength of which we can dial. And we can measure the magnetization of the sample. In case of cobalt, only metallic cobalt is ferromagnetic. The oxides and the metal support compounds are not magnetic. So if you see magnetization, it's due to the metallic cobalt only. Very nice if you want to look into oxidation events. So at full throttle, it's 2 Tesla here. We're magnetizing all the crystallites of the different sizes. And we call this saturation magnetization. This gives us an idea of what the degree of reduction is at any point in time, or how much metallic cobalt is present in our sample. As you remove this, you can find the following scenario that the magnetic moments are completely randomly distributed. And in this material we call superferromagnetic, or this behavior, which is limited to relatively small crystallites, but you do see that sometimes. In that case, we can use the so-called Rose-Werner method, which predicts the magnetization as a function of crystallite size. Here's the corresponding equation. So if you have this behavior, you can actually extract crystallite size distributions, and we've done this in some of the examples that I showed you here. But very often you see, and you can't see very clearly here, this hysteresis behavior. So it opens up your magnetizations as you ramp up and down. And this is due to large crystallites, which upon removal of the maximum field are still magnetic. So large crystallites are still displaying magnetization, and we can calculate the percentage as being, we call it gamma, 2 times the remnant magnetization versus the saturation magnetization. So all that we have to do is to do 2 quick measurements. It takes us 2 minutes in order to get this value here, and it gives us some idea as to what the percentage of large crystallites is. And should that increase, then we have obviously a sintering event at play. Okay, let's go into the examples now. We're starting with one which touches on oxidation mostly, but metal support interaction or the formation of metal support compounds may have occurred as well. Here we're using a reverse Micheal method in order to make model catalysts, cobalt particles of different size, cobalt oxide particles. There's basically a precipitation here, and you can manipulate the size via dialing the water surfactant ratio ultimately. You calcine the material ultimately after some washing, and you resuspend it in water and mix it with an aluminum support, and you're getting a model catalyst. This is the unsupported material, XRD. You can clearly see the 2 different sizes that we have obtained. Here, this is the material deposited onto the support that we ran in TPRs. You don't see any high temperature peaks, so there's very little metal support interaction by design, because it's basically a physical mixture of nanoparticles and the support. We did some XRD measurements with that, where we mimic different conversion levels. These are the large crystallites here. We did this with this XRD cell, which we specifically developed for this. It's also on display at the exhibition stand. This is the large particles that we used here, and we increased the water levels. The syngas pressure was only 1 bar, but in doing so, we're mimicking very high conversion levels, beyond 90%. You can clearly see there's no oxidation happening here. Whereas with the small crystallites, you can see that the FCC cobalt is going down here upon the introduction of water and reforming cobalt oxide. Clearly, oxidation is a function of crystallite size. No sintering during these measurements here, so we're able to size what we see here. Only there you see a small increase, but that's due to the fact that you're forming an oxide now from the metal. We did the same experiment in the magnetometer, but with different crystallite sizes or different reaction conditions. what we do here, this is at dry conditions, no water present, very high space velocities. You can see no change of magnetization basically, and here upon introduction of 6 bar of water, on top of the 10 bar, which mimics around about 2/3 conversion, or at 67%, you can see that the small crystals are oxidizing and the large ones are relatively stable. If you stick this into this thermodynamic plot here, we're here. You can see that indeed we're touching that line and this is where oxidation seems to be taking place. So oxidation, clearly size dependent. What else can we find out? Let's look into that interplay of sintering and oxidation, which has been put forward by some, and see if we can learn something about that. Here we used a cobalt catalyst on exfoliated graphite, which we derived by a sonication of graphite powder in NMP. Did a size selective centrifugation here, and it's the material that we obtain, these properties here roughly. And then we use another method in order to get these kinds of cobalt oxide particles. It's a sol gel approach via benzyl alcohol route, which employs, or which basically is a non-aqueous heat treatment of dissolved cobalt acetate in benzyl alcohol in the presence of ammonium hydroxide. Again, via manipulation of the parameters, you can get different sizes here. But ultimately, you're getting this material after some washing and drying, and we deposit it now onto the exfoliated graphite material that I showed you just now. This is what it looks like after reduction, and that's the material that we end up with. 6 nanometer particles, roundabout. The size distributions are relatively narrow. You've seen some of the histograms earlier on. And now we test this material in syngas at these conditions here, and we're increasing the water to hydrogen ratios as we step up this blue staircase here. And you can see initially there's some demagnetization, which is mostly due to the interaction of carbon oxide with the surface for the first time. Then it's rather stable, but at some point, well, very stable actually, you're seeing a demagnetization here. So there's an oxidation event, and it's stable to start with, but then you can see that demagnetization is going up again. So that's very, very strange, without us changing anything here. So could this mean that these small particles have indeed formed larger particles, which are then easier to reduce at reaction conditions and give you a large metal particle? Let's look into the gamma value, and indeed there seems to be some evidence that that may well be the case, because at this point here exactly, where we assume that growth may have happened, we do see that the gamma value is going up. On top of that, we can look at the performance figures of the catalyst. This is relative conversion levels. Remember, the actual conversion levels are very, very low, so we have to normalize things here. You see rather 100 here, and then with this event, you can see that we're losing the activity, and this is irreversible, even though the magnetization does come up. So we have lost dispersion in the order of 50%. We have seen growth from 6 to 10 nanometers, and that correlates very nicely with each other. So what has happened is that we came from down here, we moved our way up towards the curve, but then the system has moved away from it, so it has escaped oxidation in doing so. All right, there's another example that we used here, and here we're looking into oxidation only, so there was no other thing at play. We used solid carbon spheres derived by pyrolysis of acetylene. We used the same particles. These are the nanoparticles here. These are the carbon nanospheres, and that's after depositing those carbon particles onto the carbon spheres. These are the corresponding XRD scans that you see down here. We again reduce the material. It's quite nicely spread out actually, so it's a very nice model system. Also under the microscope behaves quite friendly. And then we test this material with respect to how does it behave in different water to hydrogen ratios. And first we do this in the absence of carbon monoxide. And this is the magnetization as function of time. As we increase the water levels, you can see initially it actually goes up a little bit. And that is a known effect when OH species absorb on the cobalt species, magnetization does go up. Well, it's certainly not oxidation. At some stage you can see it's going down slowly, but it doesn't really want to oxidize very quickly as you do these different conversion conditions here. As you remove water, you can see we're shooting up immediately, so it's clearly reversible, whatever has happened here. We're now introducing some carbon monoxide, firstly at low levels. Here, this is because we have carbon monoxide absorbing, and that immediately gives you a suppression of the magnetic signal. Then we're introducing water, and you can again see a very slow oxidation. And then as you take out water, it comes back up, and as you take out CO, you come up to the original levels. Everything is very reversible here, but oxidation is very slow under those conditions. The last condition is we go to higher CO partial pressures and higher syngas total pressures. And now things are happening much more immediately. You see the immediate change of magnetization upon CO introduction here. You can see, as we stepwise increase the water levels, you can see demagnetization, oxidation happening of your sample. You must remember it is a size distribution, even though it's narrow, so it's eating up the small particles most likely. And then you can clearly see as you're removing the water, the level comes back up, you remove CO, you come back to the original level. So in the presence of CO, oxidation is much more spontaneous as it is in the absence of CO. What we do believe, these are the activity features that we obtained here, everything was reversible. What we do believe is happening here is that at these conditions, and these three experiments were done back to back, oxidation is rather slow, and oxidation by water, I mean. Whereas here, where there's more CO around, this oxidation can be much faster. Which seems to suggest that oxygen CO and water, there's an interplay between the two when it comes to oxidation. Last example, I'll be very brief, I'm running out of time, is about oxidation and the formation of metal support compounds. Here we use Stöber nanospheres as the support material. Again, this is model support material. The same method. This time we have three sizes that we deposit onto those spheres, reduce the material, and we do our studies with it. So that's what it looks like. The loads are ridiculously low, 0.5%, but the magnetometer is so sensitive when it comes to picking up metallic cobalt that we can easily do those studies that I'm showing you here. So this is now in the absence of carbon monoxide. We look at the oxidation as a function of the water to hydrogen ratios. 7 nanometer, very hard to oxidize and very slow as well because we've seen it's kinetically limited. Only in the absence of hydrogen, you can see this is water only now. Oxidation is very quick, and it's not reversible as you expose it to pure hydrogen again. You do the same with 5 nanometer particles. It's a little bit quicker in terms of the oxidation, but still not very fast. 3 nanometers is much more clear. You can see how it progresses very early at the introduction of very low levels of water already. What we do now is we go straight to this 40:1 water to hydrogen ratio, and we repeat this experiment with the 3 nanometer particle. What happens is that we see an immediate demagnetization, which we believe is due to the formation of cobalt silicates, which is followed by a slow demagnetization, oxidation, very slowly, and then in the presence of carbon monoxide, we're speeding up oxidation. Very similar to what we've seen before now, but at this point now, we're taking out water as well. And you can see in dry conditions, it's actually relatively stable. Again, an interplay between CO and water, which you can clearly see here. What we do believe is happening is, what ought to be happening is that you're forming CH2 species and oxygen species forms on the surface, which should dissolve with hydrogen. But if you have a lot of water around, this may not happen. And your oxygen may get other ideas and it forms carbon monoxide in the process. So that's the interplay that I'm talking about. I will skip the rest of the results, which speaks to the metal support interaction, because here more about that later. Okay, no, okay. Anyways, it doesn't really speak to the effect of carbon monoxide. And I want to bring out some key points here. So we've tried to deconvolute effects of oxidation and sintering mostly, and also a strong metal support interaction. What we have seen is that oxidation is crystallite size dependent in Fischer-Tropsch. We've seen it over and over again now. We have 3 examples at least. The oxidation by water only is very slow. It seems to be kinetically hindered. What I haven't shown is that the formation of cobalt silicates and other metal support compounds is relatively fast and spontaneous. But what is important to note is that it's actually in the presence of CO and high amounts of water. It's the oxygen which stems from the carbon monoxide which causes the oxidation in your material. And this is highly dependent on your reaction conditions and the material that you use. So we've been able to achieve this with our in situ equipment, and I want to thank a lot of collaborators here and the funders, and last but not least you for your kind attention.